Okay, so now what remains is we need to calculate the wave functions that correspond to these energies. First, I'm going to backtrack though, and we're going to do a certain calculation. I'm sure there's probably another way to do this, but a simpler way, but this is how I do it. So we're going to look at the raising and lowering operators. We're going to act the raising operator on the lowering operator. We're going to calculate that and see what we get. So that little factor there, the square roots, are going to pull out, and they're just going to become m to h x plus I over mwp x minus I over mwp and well, this is just a number, so it doesn't affect anything, but we have to be careful about the order that we actually multiply in here, because these are operators, not numbers. So this is going to be x hat squared plus I over mwp hat x hat minus I over mwx on p hat plus I times negative I, that's just 1 m squared w squared p hat squared 2h bar and that's just equal to I over mw, that in the middle there, negative I times the commutator of x and p, which is just famously I h bar. So I times negative I times h bar over mw, that's just h bar over mw. Alright. H bar over mw plus x hat squared plus 1 m squared w squared p hat squared. Now we're going to multiply it all by mw over 2h bar. And that's just going to say the h bar on that one cancels, h bar, mw cancels, 1/2 plus mw over 2h bar x squared plus 1 over, oops, where do we go? Yeah, no, we're good. 2 mw h bar times p hat squared equals a plus on a. I'm going to rewrite that over here just for my personal reference. I don't really need to. Alright. Well, actually, yeah, we'll use that. Let's multiply that a star on a by h bar times w. What you get is h bar w a plus a equals h bar over 2 plus 1/2 mw squared x squared plus p squared over 2m I think I missed somewhere around here. I missed a negative sign, probably with the commutator between x and p. Yeah, trust me on that one. I did. I know exactly what I did. But anyway, that was supposed to be negative. That was my bad. Now let's add h bar over 2 to each side. Well, that's just our Hamiltonian operator. So when we act on the state, I'll use bracket notation. Bracket notation, I think. I've heard it both ways. Different people like to say it different ways. Acted on the state. Well, that's just our energy levels. Equals h bar n plus 1/2 n. Which means that when you act the operator, which is a star times a on the state n, it's equal to n times that state, and it's why this thing is called the number operator. Together, so that's an important identity right there. I'm gonna write it over here. Delete this stuff. Now let's suppose for a minute that our raising operator, actually we'll start with the lowering operator. When it acts on the state n, it equals some hypothetical, we're going to say it's a real number, f sub n, it's a function of n, whatever state it is, times n minus 1. It lowers it into that state, and there's a little multiplicative factor there. Well, we're going to take the transpose Hermitian conjugate, I believe, of this, and A is not Hermitian, so it's going to be the conjugate of that, so there we go. So proof I came up with. I've never seen it in a book, but I'm sure it's widely used. Which is just Fn plus, it's like you have to equate the sides. So if we take Na plus, that's going to be Fn minus 1 squared, n minus 1, n minus 1. The inner product of n minus 1 minus n minus 1. Well, the inner product of any state with itself is just 1, because it has to be normalized, probability equals to 1. So that's just going to give us our f sub n squared. Well, we already know what a plus a does to n. You can bunch that together, what a plus a does to n. It equals n. And you can pull that out because it's just a number. The inner product with itself is just 1. So you get f sub n squared equals n, meaning that take the square root, f sub n must equal the square root of n. So you now know what the raising operator does to an actual state. We're going to use a similar procedure. Here, I'll write that over here. With a hat, the raising operator. That was the lowering operator, my bad. I think I was saying the wrong one. We're going to propose that g sub n plus 1, because it raises it, some g sub n plus, well, like the last example, we'll do n a hat equals n plus 1 g sub n, which you can just pull out there, and we're going to sandwich them together. n a hat, a star equals Gn n plus 1, n plus 1. That's just with itself, so it'll just go to 1. Oh, G sub n squared, I should have specified. Now this is a little different. We're going to do a trick. We're going to say that A times A star is equal to A star minus A star A plus A star A. It's a little trick here. You know, those cancel out and you just get that, which is just the commutator of A with A star plus A star A. We already know from that equation right there that A with A star is equal to 1. So the commutator is equal to 1. And we know that, so now we get plus A star A. Well, that's going to act on the state as just 1 plus n times just that inner product right there, which is just 1. So G sub n squared is equal to n plus 1, which means that the square root of n plus 1 is G sub n, which means that is our, these are what our, actually I'm going to write it here, A star this is what our raising and lowering operators do to the state n. Raises it, multiplies it by this factor here. Well, that one particularly allows us to do a trick. Let's start with the ground state. It's going to act on the ground state, which we know as is that right there, equals, it's going to be 0 plus 1, 1. And then we're going to act on, so we know that 0 plus 1, A plus 0 equals, and you can generate by repeatedly applying that operator there to that side there, that you're going to get the next state. And then 1, 0 plus 1, 1 plus 2, A plus squared, 0 equals 2. You just keep applying it over and over again. Well, that's just going to be A plus n 0 equals n times, say, 1 plus 3, 4, 1. Oh wait, sorry, that should have been 1 plus 1. Times 2. It'll ultimately be the factorial of n. So you can define the nth energy level, I think I got that right anyway, as applying that operator to that n times and dividing by that whole square root of the factorial of n, and it'll give you the nth energy level corresponding to that energy right there of the harmonic oscillator. Classical mechanics would say that, the particle could have any spectrum of energies. Quantum mechanics says that it can only have energies in steps of these. There's another way to derive all this with a series expansion. You could just expand and then requiring that the wave function is square integrable, you actually arrive at these energy levels. It's faster, but I think this is more fun. You weren't supposed to follow. Let's see. There's something else. Oh, and I don't know how the name is pronounced. Polynomials. It provides a general solution to this without having to apply the raising operator in times, which is tedious. Anyway, but so let's write down the results. Summarize all these results here. Write it over here. Alright. And size of 0 equals. Alright, so this is the results here. This is the possible energies that a harmonic oscillator can have. That's the energy level. That's the nth state. You apply this operator repeatedly to this ground state over here. I should say wrong marker, but anyway. And these are our raising and lowering operators. So there we go.